Welcome to HurricaneCenterLive.com. I'm Alex Garcia, Director of the National Tropical Weather Conference and Executive Producer of these programs. These programs are made possible by USAA, the South Padre Island Convention and Tourist Bureau, and Plylocks Hurricane Clips. These programs are also a team effort with Bill Reed, the former Director of the National Hurricane Center, and Tim Smith, Chief Meteorologist of KRGV-TV. And now, here's Tim Smith.
Good morning, everybody, and welcome to NTWC Live for Wednesday, April the 28th, 2021. Good to have you all with us this morning, whether you're watching us live on Facebook, on the website, on Twitter, wherever you're watching. Glad to have you along today. Well, I think it's going to be a great program again today. Well, they're all good. I think today is no exception to that. Dr. Jason Sippel is going to be with us in just a little bit to talk about the hurricane modeling, HWRF in particular, and I think he's going to have a terrific presentation. As always, I want to thank our sponsors, USAA, Plylocks, and the South Padre Island Convention and Visitors Bureau for all they do to make these events a possibility. We really appreciate their support of the National Tropical Weather Conference every year on South Padre Island. This year it was virtual, but hopefully next year we'll all be back in person on the beaches of sunny South Padre Island. Let's start with a tropical update. For that, let's go over to Bill. And Bill, I'm sorry I didn't send you the memo about wearing ties today. Somebody's got to kind of hold the class of place up a little bit, I guess. Bill Reed.
Yeah, you would have had this. I'm sorry I didn't get your message comment coming back on you right then and there. Good morning, everybody. It's a windy morning here in Texas. In fact, Tim is probably getting gusts of tropical storm force there. It's just a response to the approach of that nice upper low out in the southwest U.S. Not much going on in the tropics. In fact, there's nothing right now that's active. But I just thought I'd show you. This is the remnants. This is what became of Typhoon Surigay that we talked about a week ago when it was moving out of the Philippine Sea after reaching record intensity for the month of April down there. And it's still a well-defined circulation. Central pressures approaching 970. Excuse me. And it's going to spin itself down. The model forecasts show that the system will just meander really south of the Aleutians before eventually moving east, emerging with another upper level low, and probably bringing some late season rain into the southeast Alaskan area there. So that's pretty much it for the tropics. So at this point, I'd like to say a few words about our sponsors. USAA has been a long-term sponsor of the Tropical Weather Conference, and again this year they're our leading sponsor. They also are a leading sponsor of the Storm Science Network. The company has created an insurance product for renters to make the most of their space and money. They make it easy to cover the stuff that you love for as little as 33 cents a day. USAA, what you're made of, we're made for. And I can attest to that personally. I rented over in Miami, and USAA was my insurer for a very reasonable price. Also, we want to mention our good friends at Plylocks. Plylocks window clips are made for the ease of use to protect your windows during a hurricane. They install in seconds without nails, screws, or adhesives. They are an inexpensive, non-destructive way to protect your windows from high winds and wind-blown debris. Lock-in protections with Plylocks. And they're made right here in southeast Texas in the Houston area. Okay. It's my pleasure this morning to introduce our guest. I've known Dr. Sippel since he was an undergraduate back at A&M in the early 2000s. Jason got his PhD at Texas A&M in 2008, proceeded on to do postdoctoral work with NASA Goddard, where he continued on in a research role until about 2014, where he went to work as a contractor at the Computing Center for the National Weather Service, where he specialized in helping out with the work on HWRF, and that was in 2014 to 2017. Since then, he's been at the Hurricane Research Division at AOML in South Florida, where he's one of the lead scientists on developing cutting-edge forecasts of hurricanes using the HWRF model. And today, Jason's going to tell us where he stands in some of this work and the challenges yet ahead. So, Jason, all yours.
Okay, thanks, Bill. I'm going to grab the presentation. All right. Should see my screen. Everybody good?
We got it.
Okay. I wanted to make sure I was unmuted. Try this again. Okay. So when Alex and Bill first asked me to give this talk, they really first asked me to talk about recent H4 performance and what we could expect, coming into the next season. But really, to understand H4, you got to understand its history. You got to understand how it was developed and how things have evolved over the past 10 years or so, and to get a feel for what you could expect out of it, in why it performed the way it did last year and why it might perform the way it will next year. So that's really what this talk is going to focus on to a large extent. I'll give a history of tropical cyclone forecast improvements, in particular in relation to data assimilation development. That's what my specialty is. Data assimilation is the way you bring various data sorts, like the reconnaissance data, the large-scale observations, satellite data, whatever data set you have, into the model in a statistical sense. So from there, then I'll move to some ongoing developments, and finally, I'll close with the future direction, looking at a sneak peek at the greatest hurricane model that's being developed by NOAA, the Hurricane Analysis and Forecast System, which will ultimately be H4's replacement. So the first stop into understanding tropical cyclone behavior and errors in forecasts is to look at the track forecasts. And the reason for that is because the track forecasts have been improving for decades now. This particular graph shows the position error, forecast error at various lead times, days 1 through 5, from the Hurricane Center from 1990 to 2020. And you can see ubiquitously they're all decreasing more or less year after year. In fact, the 3-day average forecast location error now is about what the 1-day error was in 1990. It's really been a really remarkable feat in the sciences. And the reason, and if you go back, you can see this kind of improvement at the shorter lead times going back even decades before 1990. So it's really been impressive. And these improvements are largely tied to improvements in the large-scale forecasts. So here I have a graphic that shows skill, and just to get your mind around skill, it's the higher the skill, the lower your error. So you want your skill to go up and your errors to go down. In this case, I'm showing skill of the large-scale 500 millibar pattern over North America from the GFS. I guess it's whatever the operational forecast is. GFS was for a large part of that. But you can see the skill is continuing to go up at 36 and 72 hours, more or less year after year. And that's really intimately related to the improvement in tropical cyclone tracks. So that covers the track portion, but what about intensity? Well, as it turns out, intensity didn't improve for a really long time. You can see this is the same as the first graphic I showed for the track forecast, but these are intensity errors. You can see here the 24-hour intensity errors are basically steady at around 10 knots through about 2010. And then suddenly, around 2010, you can see a big drop-off in the errors, intensity errors. This is when things really began to improve. Well, why is that? Well, starting around 2010 is when the onset of the Hurricane Forecast Improvement Project began. It's called HWRF. And the biggest goal of HWRF has been to improve hurricane intensity forecasts. So that's been going on for about a decade now. And one of the significant goals of HWRF has been to develop and improve the HWRF model. So here on the left, you have the performance of the HWRF. Again, this is expressed in terms of skill relative to climatology. So the zero line means that you're just as good issuing a climatological forecast as you are actually following the HWRF forecast. So if you're doing worse than that, that's not very good. You can see in the early years, HWRF, I think, went operational in 2007 or 8, And even through, the early years, 2011, 12, 13, it was pretty terrible, actually. It took a while for HWRF to get to be a skillful model. So the early years, we're doing, at the extended, 40% worse in climatology. Then you get to the 2015 timeframe, and we're doing a little bit better in the short lead times, but still bad in the extended. And it really wasn't until the last couple of years when we had some really key developments in HWRF that we began to see a big bump up in the skill. So now, roughly speaking, the skill is around 30-35% better than climatology. So that's about a 60% improvement in skill over the past 10 years. This improvement has absolutely led to improvements in operational forecasts. HWRF is really the premier intensity guidance that the Hurricane Center uses. So it's been nice to see the HWRF investment really paying off. So the remainder of this talk is going to really focus on why HWRF has improved so much. And a big part of that is use of this data here that I'm showing in this graphic. This is reconnaissance data. This is just an example from Michael. This is all of the dropsondes, these little symbols here, these individual symbols of the dropsondes. The color-coded data is all flight level winds from all the different reconnaissance missions. You have the vortex data messages sent out here. These are just summaries of the data, basically. And you also have, this is tail Doppler radar data. So a few the NOAA planes have a tail Doppler radar on them that can give you the three-dimensional wind field in the storm. And so this is what I have here graphically displayed as a retrieval of the wind field in Michael. And this tail Doppler radar data has really been instrumental in HWRF in improving its skill. And the current skill of HWRF depends very much upon whether this kind of data is available. So taking a step back, I want to talk a little bit about the history of using tropical cyclone observations. And the first stop that's necessary is really on the dropsonde data. The reason for this is because dropsondes have been used the longest out of all the reconnaissance data going into the operational models. So starting in 1997 is when we started assimilating the dropsonde data into the global model. This figure on the left here shows a study that was done in 2010 that looked at the impact of the data, the dropsonde data globally. So they used the GFS and they did it runs with and without that dropsonde data in. And the black line gives you the global average percent improvement as a result of assimilating that data. So the zero line means you're no better than using it than not using it. Positive means you're doing better. So you can see for that study, they found that the dropsonde data improved the track forecast for global TCs around 10% in the first 72 hours, and it trailed off a bit towards day 5. This has been a common finding. There have been several dozen studies that have looked at the impact on tracks of dropsonde data, and some are better, some are worse, but it averages out to around 10%. In fact, I'm the PI on a current study using the basin scale HWRF, talk about in a little bit, where the dropsonde data has about a 5% impact, 5% improvement on the tracks. So, it's more or less, averages out to 10%. So this is still true today. We see that the dropsondes are still improving the tracks today. So that's kind of using point measurements that can be taken over a large area. But what about really the inner core data, the data that focuses on the eye wall and the surrounding rain bands of the tropical cyclone? It became apparent in 2008, and I think Bill was down in Houston at the time, that using data in a landfalling tropical cyclone, this was Umberto, it rapidly, in the morning it was nothing, maybe a little swirl, became a depression. By the evening, it was making landfall on the upper Texas coast, just northeast of Houston, as a mid-category 1 hurricane, caught everybody by surprise. And so this was a big focus of research at Texas A&M, where I went to school. And it became apparent that using Doppler velocity data from this coastal network, from Corpus, Houston, and Lake Charles, when we assimilated that Doppler velocity data into an experimental data assimilation system that we were using at the time, it tremendously improved the forecasts. I'll show you that in just a second, but here are just the observations on the left. This is Doppler reflectivity. This is the next round reflectivity versus the analysis in that experimental system. And you can see the analysis looks quite a bit like the observations in both before landfall and after landfall. It looks like we did a pretty good job at capturing the structure of the system just in the analysis. And I can tell you, if your analysis is good, that is the first key step in producing a good forecast. And here you can see the impacts. So on the top, we have, this is the intensity evolution in Alberto. In red, you can see it rapidly intensified up to 40 meters per second, about 80, 85, I think that's 80, 85 knots, I guess 80 knots or so. And then it rapidly weakened after landfall. You can see these gray and black lines are when you don't assimilate any of that Doppler data. And you can see that all the forecasts stunk. They were terrible. And that was what the operational forecasts were at the time. Nobody had a clue that this was going to happen. However, you can see down at the bottom panel, when you assimilate that Doppler velocity data, all your forecasts, you can see they follow, they're not perfect, but they do give a good representation of the rapid intensification of the storm. So this is our first clue that, wow, using this Doppler velocity data can potentially have a really big impact on the intensity forecast. So that single study led to a decade or more long investment into how we could use the Doppler velocity from various resources to improve forecasts. And one of the big ones was from the NOAA aircraft. Like I said, they have a Doppler radar on the NOAA aircraft. So this same system, that same experimental data assimilation system, was used to assimilate Doppler velocity from the reconnaissance missions. And a fairly large sample of tropical cyclones that occurred over roughly a 5-year period. And you can see here is the error, again, days 1 through 5, the error, the forecast error. These are operational forecasts in the kind of thin gray and black lines versus that experimental system, the thick black line that added the tail Doppler radar data. And you can see the radar data has a really, really big impact on the error. Now, we'll say that some of this improvement is due to the fact that it was an experimental advanced data assimilation system, and it was just a better model. But that's not all of it. They directly showed that assimilating this radar data had another incremental impact just upon the improvement in the model itself. So these results from this study then led to a dedicated effort to assimilate that tail Doppler radar operationally. And got my slides. Oops, I might have missed a slide here. Okay, so anyway, this slide gives you a history of the HWRF improvements from 2010. This is basically a decade's worth of improvements in HWRF. And you can see in red, I have, this is specific to data assimilation. So in red, I have when various data specific to reconnaissance was added. The red text. So when the green box, so when the box goes from green to red is when that was added. So you can see that P3 Doppler velocity was added in 2013, as well as some dropson data. In dark black, bold, you see various improvements to the data assimilation system. So this warm start HWRF ensemble, fully cycled DA, you don't have to understand what all that means, but those are big deal, big ticket items, big ticket improvements in HWRF. So there have been a handful of them. So by 2018, we were getting all the reconnaissance data in, and roughly 2018 to 2019 timeframe, we had a data assimilation system that was really getting to be almost state of the art. It was finally getting to the point where that experimental data assimilation system back in 2008 to 2010, that was getting those good results. We finally got HWRF to that point by roughly 2018, 2019 or so. And then by 2020 is when we finally started assimilating the Doppler velocity data into HWRF. So current observations used in HWRF, well, we have conventional data such as radiosondes, dropsondes, aircraft, ships, buoys, surface observations, scatterometer, etc. Importantly, now we also have that 88D Doppler velocity, which I showed to be very important. The big ticket, though, this red, I have this in red because HWRF is the only model in the entire world that assimilates all of the reconnaissance data coming from the planes. The dropsondes, the TDR, SFMR, flight level, everything. Some other models, GFS, and I think the ECMWF, some of the other models, they assimilate some of the data, but not all of it. So that has a big impact on HWRF. And also we're assimilating the atmospheric motion vectors that come from satellites as well as clear sky satellite radiance observations. So how does the recon data in particular, because I've been harping on it now for a few minutes, how does that impact HWRF? So this graphic here shows an assessment we did for the 2019 version of HWRF. The assessment was actually done in the fall of 2018, but it was a developmental 2019 version of HWRF. And here are the errors you can see on this graph on the right, with and without the recon. You can see when you have the recon, at most verification times, especially before, adding before 72 hours, your intensity forecast is doing better than when you don't have it. And it winds up being about a 10 to 15% improvement. This sample was taken, we looked at the major storms from 2016 to 2018. So this was Matthew, Irma, Maria, Florence, Michael, and Harvey, I think. And why am I saying that? Because major hurricanes tend to have they tend to be the hardest to get with data assimilation. The really tight gradients in the inner core, the strong winds, you have to do really well with your model physics in order to get that right. And you have to sample it well, and your data assimilation system has to represent the storm well. And the only way to do that is to invest a lot into CPU. And so it's taken a while to get us to that point. But if you're doing well with major hurricanes, that's kind of like the gold standard. Doing well with tropical storms is a lot easier than with major hurricanes. So it's really encouraging to see that with these major hurricanes that we're improving so much of the forecast, the intensity forecast with the reconnaissance data. So now, the HWRF is, now that we know, we've proven that the reconnaissance data can actually have such a positive impact on the forecast. Interestingly enough, HWRF is now being used to change how the reconnaissance is gathered. An example of this is with the G4. Prior to 2018, the G4 would typically sample the large-scale environment. So here on the top, you have typical locations of G4 drop zones. You can see away from the storm would be at the red dot, and you would have these white circles would be where you would have environmental sampling. Before 2018, you had a lot more of these white circles away from the storm, and you only had one ring around the storm. This outer ring would be around the storm. The inner ring was never done before 2018. But there was some evidence to show that if you brought these drop zones, some of these drop zones from the environment closer to the center of the storm, you do two things. One, it tends to impact the track more if you're closer to the storm, but also it has a really big impact on the intensity forecast. And we've definitely shown that with HWRF, that the more you sample here in the vortex, the better your intensity forecast is. We've also know that the G4 has a Doppler radar on it. So getting that Doppler velocity data in is crucial. So when we started assimilating that data from the G4 into H4, it was even more motivation to bring the G4 flight pattern in to this inner circumnavigation. And you can see down the bottom, these are wind retrievals for the G4 TDR. This is from the same mission here. These retrievals are from this inner circumnav from the G4. You can see that's a big area of data going into the model that previous to 2018 wasn't happening. Another thing that we started doing in 2018, it started experimentally in 2017, implemented in 2018, was endpoint drop zones for the C-130 missions. So here on the top, I have a graphic that shows what a typical alpha pattern for the C-130 might look like. And previously, prior to 2018, most of the missions just had, at the center of the storm, you had the star, you'd have drop zones in the center, maybe at the radius of maximum winds, just a bit out from the center, but definitely nothing at the turns where these black dots are. So I worked with the Hurricane Center and suggested, they should try dropping drop zones out here because we know that the reconnaissance data has such a big impact. And so they did. Then we did data denial experiments on these tests. And that's on the bottom here, you can see the impact of adding these drop zones at these locations in the model on the intensity forecast. So positive is better, negative is worse. And you can see we're roughly, in the 5 to maybe 10% on average improvement due to adding drop zones at these locations. So based on this work that was done in HWRF, this practice was implemented operationally in 2018, and now all the C-130 missions have dropsondes. So we've really substantially increased our dropsonde usage due to really experimentation with HWRF showing what a big impact it has. So I showed you the impact of reconnaissance evaluated in the 2019 version of HWRF, and here I have an assessment of how HWRF does. This is the 2020 version regionally, and this is really an interesting look. So I was really interested in knowing, aside from, okay, I have the direct assessment of the impact of reconnaissance, but overall data in general, how does the model respond, or how do multiple models respond to having data versus not having data for the intensity forecast? So I wanted to look at the skill in two different regions: near CONUS, which is this kind of dark gray region, roughly within 700, 800 kilometers of land, really well covered by the P3 and other reconnaissance. So the various colored circles here on the left show you where we most often fly the P3. We can fly outside those regions, but that's, certainly those areas are capable of having very good sampling for recon missions. But also equally as important as reconnaissance is really near CONUS in the Gulf of Mexico and, closer to the U.S. in these gray regions. They're close enough to be directly impacted by the U.S. Data network. We have, hundreds of weather balloons sent each day, and when there's a major U.S. threat, they're released four times a day, not just twice a day. We have planes that are flying all over the place over the U.S., and those planes transmit data that are assimilated into the operational models. There's just all kinds of data. In HWRF, we have the 88D network. So all this data is getting into the model. So, aside from the reconnaissance, just, how does all this data impact the intensity forecast? So I have near, and I have out in the main development region, MDR, where, we do get some reconnaissance missions out in the western MDR, but generally speaking, the MDR is pretty data sparse. Most of the time we only have satellite data, atmospheric motion vectors and radiances, and I guess ASTAT surface winds, and that's if you're lucky. There's cycles when those data sources just don't get into the models because there's not that satellite isn't there at that time. So how does this impact the forecast? So on the top, I have the intensity skill relative to climatology for HWRF in black. COAMPS TC, another really good intensity model, does not have its own data assimilation. It just relies on the GFS, and then it has a scheme to initialize the vortex, but no data assimilation. And then IVCN, which is a consensus product, which in general, IVCN is if you average over the season for the whole sample, IVCN is better than the individual inputs. So the consensus is kind of what the Hurricane Center tends to go towards, unless they have a good reason not to. So I have the intensity skill for these two regions. In the bottom, the MDR, and the top near CONUS. And the first thing that you notice right away is that the lines, all three of these lines near CONUS, are way, way north of where the lines are in the MDR, meaning the skill, the intensity skill, is much, much higher as you get towards CONUS than out in the MDR. And I can attest to, I have seen many, many major busts on the intensity forecast out in the MDR where HWRF would show a category 5 and it's a weak tropical storm. HWRF is notorious for that. And it's a reflection of the fact that, there's physics biases, but we just don't have data. So the skill near CONUS for all three, IVCN, COAMPS, and HWRF is much higher. What's interesting, though, is if you compare just between the three lines themselves. So out in the NDR, COAMPS and HWRF, they trade. They go back and forth. HWRF's a little better in the shorter lead times. COAMPS is better at the longer lead times. But on average, they wind up being about the same, both worse than the consensus, as on average things are. Consensus is kind of doing what you'd expect to do. But as you get into CONUS, near CONUS, wow, well, this really changes. Now, asterisk here, I evaluated this sample only over water. One of the things about HWRF is it doesn't do as well with track, and so I wanted to filter that error. So I was really interested in, okay, how are the models performing specifically over the most interesting aspect of the forecast, which is over water. And so that kind of gets that land impact out of the way. And you can see, lo and behold, wow, HWRF bumps up above the other two in the over water portion of the forecast near CONUS. And I can say that I am 100% confident that is due to all the extra data going into HWRF that is not going into, for example, COAMPS. The skill is way higher on HWRF than COAMPS. And COAMPS, since COAMPS and other models are constituents of IVCN, they actually, in some sense, kind of drag IVCN down for the overwater portion of the forecast. So HWRF kind of stands out as doing better than the consensus just because of all this extra data that's going in. So that takes us to I want to give some specific examples where you can see that HWRF kind of did better, and this is really focusing on 2020. And so I have a few storms here. In the lower left, you can see the date and the cycle. I grabbed these graphics just from the EMC webpage, so they're not all consistent, they're mostly consistent, but in the black line, you have what was the operational working best track. In purple, you have the HWRF forecast. You can see HWRF struggles with track more than the GFS does, for example. Red is the operational forecast. Orange is COAMPS. So this was one of the earlier cycles from Hannah, a storm that rapidly intensified to a hurricane off the Texas coast, another one of these Texas rapid intensifiers. You can see really starting out from the early tropical storm stage, we were getting the TDR data in, and HWRF was advertising a threat for a hurricane. It wasn't quite there in the first cycle that I show here, but it quickly made it there. So black here, this black dot shows the landfall intensity. This particular graphic, they didn't have the full working best track on it, so I had to fill in what the landfall intensity was. But you can see this is a really good forecast from HWRF. It gives roughly the right landfall intensity within 6-12 hours or so of the right time. So this is really encouraging to see this performance. Here, this is even better. Really a very good forecast of the intensity, and it just kept it up really the entire time. So that was a kind of a first clue. Wow, we're really doing well here. You move on to Laura, and in some sense, this is even better. It's really, really hard to get forecasts of major hurricanes right. Category 4. Laura was almost a Category 5, and HWRF struggled as it was out over the MDR because Laura started here, east of Puerto Rico, and some of the initial HWRF forecasts were pretty terrible. The track forecasts were into South Florida as a major hurricane, which obviously didn't happen. But as we got more and more data into it and it got closer to the network, the track forecast improved a lot. And lo and behold, as we got over Dominica, look at this forecast. This is still a moderate tropical storm, and it has the landfall intensity, within 5 knots for, near Category 5. I mean, that's really spectacular. Not all the forecasts were this good. Eventually, COAMPS TC caught on, and, this is another good, the timing's a bit off, but the intensity is right, as it was south of Cuba. Some of the later forecasts were a little bit weaker. They were borderline Category 3 or Category 4, but I'll tell you, if your NWP is sitting at roughly a Category 4 and a weak 4, and it comes in at a strong 4, you're not doing too bad. That's pretty good compared to where we've been in the past 10 years. So you can see it just continued to perform well through Laura. Sally was a struggle. So this is kind of a really big flashing red of okay, HWRF gets the intensity evolution, but the track really stunk with Sally. And so the timing of the intensification was off and the track forecast was off. So here you have, okay, it made landfall as a mid-2, and it shows a mid-2 making landfall, but at the wrong time, at the wrong location. It brings it into New Orleans. So that's something where we struggle with and needs to be continually developed. This forecast, some of the later ones came in too strong. I can say this particular cycle, I think maybe there's a data issue in this cycle. It was rapidly intensifying too fast, and again the track was way off. But it gave the right idea that something would be rapidly intensifying as it approached the coast. It just the timing was off. Later forecasts were a little bit better. You can see HWRF and HMON were kind of both trading places on how much the intensification would be. Columbus lagged behind. It was always too weak for Sally until just really in the last day or so before landfall. Here's the landfall here. As we got closer to landfall, the forecast got a lot better. Delta was, I would say, generally fairly successful for HWRF. It generally showed a category 2 making landfall in Louisiana, even from some of the initial forecasts way down here in the Caribbean. There's some problems in this, kind of around 48 hours or so, because it did not appropriately make landfall in the forecast over the Yucatan, so that caused some intensity biases. But as we got near the Yucatan, you can see this is a really good intensity forecast. Evolution very closely mirrors what actually happens in the working best track. And as we moved off the Yucatan, this is an excellent intensity forecast. This just wasn't possible 5-10 years ago. So continued good performance throughout. Data is another good example. The initial forecasts were bad. The track was bad. It didn't make landfall in the Yucatan as it was supposed to, so that kind of screwed things up. But as we moved closer to the Yucatan, again, another example, as we got more and more of those TDR emissions in, here, look at this. Just before the Yucatan landfall, look at that intensity evolution. The purple line is very close to the black. So this is something that you just wouldn't have seen a couple of years ago. And really, so here, as it moved off, it was advertising a week 3. What came in was really a strong 2. That's a pretty good forecast. So that gives you an idea of where we were last year. I focused on Gulf storms because that's where HWRF really does the best. So, I talked about some problems and I talked about some successes. So, what are the ongoing developments? Oh, one of the things that we're looking at closely in NOAA is drop signs. So NOAA's acquired another high altitude jet to replace the G4. The G4 is becoming less and less reliable as it gets older. So we have a G550 coming online in 2023, I believe. And it's going to have all the capabilities of the G4 plus some. It can fly higher, so we can get, it's more versatile near the storm. We can fly over the top, closer into the storm, over the deep convection a little easier. So that's really important for gathering data. It has a longer capacity. We can fly longer if we need to. And it's going to have other instruments on it too that potentially at some point in the future could become operational. We're also looking at the impacts. We're doing a major cost-benefit assessment of drop zones currently underway using the basin scale version of HWRF. Now, I mentioned HWRF has improved a bit since the results I showed you with the recon impact assessment. And this is really showing. So we're finding on the right here, this is the intensity impact in that assessment just from drop zones. So all drop zones, these is intensity error, all drop zones in green, no drop zones in red. And you can see this green line is solidly below the red line with some statistically significant results at a few of these days, at these verification times, which getting statistical significance with intensity is really, really hard. It doesn't happen too often. So this is kind of a big deal. So this is just all versus no. The entire project, I'm a PI on this project, is evaluating, which sondes, like away from the vortex, in the environment, near the vortex, inner core, where should we be dropping? But it turns out that removing drop zones anywhere has negative consequences one way or the other. So really, we should be dropping drop zones as much as possible everywhere we can. So it's an interesting result, but I think it gives NOAA some guidance on where we should take things in the future, because drop zones aren't free. They're $850 a pop. So it's good to know that they're having this kind of an impact. Another big deal is the GFS 16 upgrade. So GFS 16 is going to make quite a bit better use of the reconnaissance data than GFS 15 did. It was upgraded in March, and we added a bit more drop zone data into the model, and additionally the flight level HDOP data. And this is the impact on the GFS track shown here, expressed in terms of percent improvement. So if you're positive, that means that GFS 16 is better than GFS 15. Negative would be worse. You can see all of these verification times through day 7 are all better than GFS 15. This is just as a result of, I'm sorry, these are both GFS 16 with and without the with and without the HDF, the additional dropzone data. You can see that that data improves on average the tropical cyclone tracks over the North Atlantic, the entire basin, whether or not the data was in a storm or not, over all cycles, all tropical cyclones in the North Atlantic, by about 5%. Now, if you just narrow the focus down to the cycles where the data was in, the improvement's a lot better. So we're going in the right direction here, right? We're adding this data into GFS now, and when we're dropping the extra, when we're assimilating these extra drop zones and assimilating that flight level data, we get a big boost in improvement. So I think you're going to see going into 2021 that GFS, the track forecasts are going to be quite a bit better. I don't know if they're going to be, as good as ECMWF. That's always been the big comparison, but they're certainly going to be better. Maybe as good as ECMWF, we'll see. And that's going to have an impact on HWRF as well. GFS track impacts HWRF track. And you can see that here. This is an assessment of the 2021 version of HWRF compared to the 2020 version, specifically the track. So again, this is percent improvement. And where you're positive, H221 is better. Where you're negative, it's worse. Across the board, H221 is going to have appears to have better track forecasts, roughly on average about 5% than H220. I expect near CONUS to have better intensity forecasts because we've improved the use of the 88D data in H221 compared to H220. So that didn't show up in the overall sample, but specifically near CONUS, where we're most interested in having good forecasts, I would expect pretty darn good performance out of HWRF this coming year. So that's HWRF. That's where we are with HWRF. But what about the next implementation? Where are we heading in the future? And we've got some really exciting news coming from NOAA. We have the Hurricane Analysis and Forecast System. So this is just one screen grab from an active period of the 2020 season from HAVS. These are just kind of test runs of the HAVS system. And in 2020, HAVS was just cold started off the GFS every cycle. There was no data assimilation, just cold starts off the GFS, but the forecasts were pretty good. We're developing and test running the data assimilation system in HAVS right now and getting decent results. One of the big improvements of HAVS over HWRF is shown here. So HWRF runs individually for each storm. So for Laura and Marco, for example, there is a different instance of HWRF running for each storm. The storms couldn't interact as they naturally should. And here we have 17, 19, 20, 21L. All these storms have impacts on one another, but in HWRF that doesn't happen because they run individually. But in HAVS, that does happen. And that should have a generally positive impact on the ability of HAVS to perform better than HWRF. There's additional benefits in HAVS. One being because of the way it's formulated, because of the way of the domain is set up, it has a more flexible, capable data assimilation system than really would ever be possible in HWRF. In particular, we're going to make much, much better use of satellite data. This is really important because reconnaissance is only available a small percentage of the time near CONUS. As you get out over the Atlantic, you saw the HWRF forecasts aren't as good. We don't make very good use of satellite data in HWRF, the little data that we do have. And so that's a big area ripe for development, and HAVS, that's going to be a major focus. So we're going to have a huge effort going on there with the satellite data. And again, like I said, realistic storm interaction that's not possible in HWRF. The result, we should have better initialization of the storm in the environment and improved track and intensity forecasts. So in conclusion, the NOAA TC prediction is really undergoing dramatic advancements led by improvements in the global models and HWRF. We're using more and more of the available data in data assimilation, and we have long-term plans to address some of the weaknesses I've talked about to allow for even greater data usage. And finally, all of the above factors really should contribute to better forecasts and from intensity in particular. Well, that's all I have.
That's great stuff, Jason. Thank you. It's encouraging and fascinating to see all the work that you're doing and encouraging to see those improvements. 5% can make a big difference, 10% even bigger as we continue to go forward. We got a bunch of questions coming in online. We'll get to those in just a second. I know Bill's got a bunch of them as well. Before we do that, though, we do want to thank our sponsors who are part of this once again. Questions in just a second. One of them, the South Padre Island Convention and Visitors Bureau. From the beach and water lovers to the adventure seekers and kids of all ages, the city of South Padre Island says past and present visitors know that SPI is fun, and perfect. The island encourages people to plan their escape and come visit. South Padre Island is so ready for you. SOPadre.com. SOPadre.com. And also Blackmagic Design. Blackmagic Design's 810 Mini line of live production switchers makes it easy to create professional broadcast quality programs and multi-camera productions and stream them live. Simply connect the 810 Mini to your video sources and go live with up to 8 sources. The 810 Mini line works with any streaming software, and the 810 Mini Pro and Extreme can stream direct to social media. For more information, visit blackmagicdesign.com. All of our sponsors help make this a program a possibility. Those are two of the big ones. Usually we're on South Padre Island. I have space there where we spend a lot of time, and it's a great place to be. Okay, Jason, let's start with some of the questions coming in online. Let's start with this from Marcel. He says, what about the interaction with land? Any ideas how to improve? Because you talked about once it interacts with land.
Yeah, so what I did not show was that HWRF has known physics issues over land. Can you hear me?
Yeah, go ahead and stop sharing your screen so we can see you.
Oh, yeah, sure.
There we go.
Okay. So HWRF has known physics issues over land. For the last 10, 15 years, it's really been developed with a focus over water. And we've really begun to see over the past few years that the track, as it gets near land, there's major track problems. And we have the University of Utah has done some work that's shown that there's some planetary boundary layer physics issues that need to be fixed. And we're also not assimilating a tremendous amount of METAR and mesonet data. And I am leading a study that's looking specifically at adding the METAR and mesonet data into HWRF, and I looked at about 150 cycles, and it improves the track forecast by about 10%. So right there, bang, right away, there's something we can do to improve the near CONUS forecast. That being said, I'm not sure in HWRF what is going to happen with this, because there's not going to be a model upgrade. We've already made the 2021 HWRF. There's not any more upgrades coming into the summer. Next year, I'm not sure if there's going to be a model upgrade because of work on the INSEP supercomputer. And then we get to 2023, and that's the first year of halves. So this work that I'm doing in HWRF, it will be put into halves. But I am not sure that if there's going to be another upgrade to HWRF or not. So one way or another, we're going to get better near land forecasts, but it may not be in HWRF. So we'll see.
Great. Good question from Marcel. Thank you for that. Bill, jump in. I've got some more over here, but let you jump in and ask a few and then come back over here for some more.
Great. Fascinating talk. I guess one of the questions that come to mind is that the reconnaissance data as it stands now, there's just the two aircraft, the P3 and the G4 or its successor. They'll have the Doppler wind type data that seems to be leading the improvements. Are there any thoughts on what kind of proxy data from satellite might be able to serve that purpose?
Yeah, so there is nothing from satellite that gives the same data that we get from the intercore winds as of now. Maybe 50 years from now, yeah. That being said, there is work that has come out of the Penn State group, and that's the same group that produced my advisor back when I was in grad school. We're working with to do all these impact assessments of the Doppler velocity data. They've used satellite radiance data, and they have innovative ways of using satellite radiance data from the GOES satellites, and they the intensity forecasts in their experimental system. So it is likely going to be that even though we don't have the same form reconnaissance that we do have satellites, there are ways to milk the satellite data to get improvements that we just haven't used so far. And are you all having problems hearing me? They're mowing the lawn.
No.
All good? Okay, good, fantastic.
Sounds good, but I'm old and deaf, so who knows, right? You didn't specifically mention rapid intensification, but and I chatted with you off and on during the season on what I thought were some pretty good hints at RI from the HWRF model. What's your thoughts on the ongoing challenge of RI, which is vitally important in the Gulf?
Right. So honestly, one of the challenges is the way we verify RI, which is kind of a quirky thing to talk about. But typically, with the way we verified RI in the past is, well, if if your model says RI, now, and it doesn't happen to 24 hours from now, that's a miss, right? But if you take kind of a bigger picture view and say, okay, if your model says it's going to RI and it RIs within kind of a bigger time frame, if you look at that, verifying RI that way, and look over the past 10 years, the RI from NWP has improved tremendously. Unfortunately, that doesn't meet the threshold from the Hurricane Center because they need to know when it's going to RI. So, we're moving in the right direction. The timing issues, I think at some point we're going to have to move towards ensemble forecasting. This deterministic forecasting is where we just have a single run. It's subject to tremendous challenges because RI is inherently a stochastic process. There's so much uncertainty in timing. So if you have an ensemble forecast, I think you can have a much better sense of what the potential variability is and get kind of an envelope view of when the RI is most likely to occur. And I think ultimately that's going to help improve the operational forecast the most.
Wow. Question on the HWRFs. What's the resolution going to be?
So the current resolution of HWRFs in this big domain is 3 kilometers, which is HWRF is running at 1.5. So we just can't possibly run a 1.5 kilometer grid over that big of an area. But eventually HWRFs is going to have moving nests in the same sense that HWRF does. But the difference is that HWRF doesn't have that big, huge static nest that HWRFs does. So, eventually we're going to have a higher resolution for HWRFs, but really it's doing pretty good right now, even with a 3 kilometer, even though it's not as fine resolution as HWRF. So I think, as we move towards higher resolution, you're going to see HWRFs. I think we're going to get to like 4 years from now, HWRFs is going to be blowing HWRF out of the water on the intensity and track forecast. You're going to have one product that's having really good forecasts for both.
Sounds great. I'm sure you've seen a little news blurb a month or so ago about a hiccup in a research project to employ phased array radar on a reconnaissance aircraft. I looked into it a lot afterwards, and it seems like a must-do thing because the intent is to embed one on a research C-130, which, if it goes the same route as the Smurf, you'll be able to eventually migrate those onto the operational C-130s and get an extremely large increase in the amount of data available for the modeling.
So I can say that NOAA is exploring ways to move the phased array radar forward. In fact, I had just spent Monday and Tuesday, most of the day, on telecons discussing the replacement to the P3. And that's coming roughly in 2030. Sounds like a long time from now. It's just like tomorrow, basically, and the way these things happen. And one of the big discussions is, what are our radar needs compared to what they are today? And yes, we're going to need the tail Doppler radars are great. We need something better. And the phased array radar is very likely something that, it's a strong contender. And NOAA's going to find a way to make it happen. But we'll just, have to see how it all falls out.
Very interesting. Yeah, Tim, back to you for some more questions from the crowd.
I've got one, and sometimes I like that I learn so much from our viewers as well. And I'm not sure what this project is, but Casper's asking how the new Alamo project will impact the HWRF. I don't think we're talking about San Antonio.
Alamo, those are the floats, right? So HWRF does not directly assimilate ocean data. HWRFs will. If there's any additional data going into the ocean, it's gonna indirectly. There's an ocean there's an ocean DA system that's run, and the output of that is then the initial conditions for the HWRF ocean model. So there will be an indirect. If there's additional data going into the ocean, it will, indirect, but of course it has to be assimilated. But yeah, this is a big ocean initialization has become a really big area of study. In fact, some of my colleagues just did a study using an advanced version of HWRF that has a different ocean initialization. They assimilated salinity data from the Amazon outflow region, and it turns out that the salinity of the ocean water has a huge impact on how much overturning there is in the upper ocean, which in turn impacts the heat potential, the heat mixing, which in turn impacts rapid intensification. So they're getting really big improvements in forecasts, and they've seen this with other storms as well, when they use a better ocean initialization. So this is something that is more applicable to HAVs, something that we're moving to in the next 5 years or so, but it is going to be a big deal.
My last question, then I'll go back to Bill to wrap up on that end. But is you've seen significant improvements in the last 10 years. 10 years from now, the new whatever the P3 new version will be out. The G550 will be out. Models continue to improve. Where do you think we can be 10 years from now?
Yeah, that's a good question. So what you can't do is you can't do better than the uncertainty in the observations, right? So right now, the NHC roughly, James Franklin did a study on this, on the uncertainty of the NHC, what their best track assessment is, right? And so when they don't have reconnaissance data, it's like roughly a 10% uncertainty. Bill, what is it? Is it 10% or 10 knots? I don't know. It's pretty big. So it's
10 knots.
10 knots. Okay, so there you go. So, at some point, like from a statistical standpoint, we're not going to get, we have some ways to go. Like the average intensity error at HWRF is roughly around 15 knots through, the watch warning period. So, we can get down to probably around 10 knots. We have a ways to go, but we definitely can't go lower than the uncertainty in the assessment.
That makes good sense. Okay, Bill?
Yeah, I just have one quick question, and then we'll have to wrap it up. What kind of horsepower are you going to need on the computers to do hurricane models on an ensemble?
More than we have.
Good answer.
It's really, we're constantly hamstrung by computer resources. We can do more now. I mean, we can't do as much now as our potential, because there's just limitations to CPUs. And even HAVs, in a deterministic sense, probably is not going to have the CPU resources for a single run to really milk out the best intensity forecasts that we could produce. So that's not even talking about ensemble. So I don't know, maybe 10 years from now we'll have enough CPU resources to do limited ensembles with a really a configuration that has a very good deterministic forecast set up, as well as some limited ensembles. I'm not sure, but it's not going to be in the next few years for sure.
Yeah, I think the big thing you'll see in 10 years is you'll have better structure forecasts, which will lead to better impact forecasts at landfall for the wind field and from the storm surge.
That is honestly, to me, that's a bigger deal than getting the maximum peak intensity right, is getting the structure right, because the number one killer, as we all know, is storm surge. And if you can get a good structure forecast and get a good wind field forecast, you're going to improve your surge forecast, and that is a really, really big deal.
Cool. A recap on one of the storms. We have one of the very interesting events.
Yeah, sounds good.
Good.
Thanks for having me.
Okay. I'm going to finish up here with another plug for USAA. USAA makes insurance products for veterans, being one. I can attest to that. So when an Army family got a little surprised, they didn't panic. They got a bigger car for their soon-to-be bigger family. Then they called USAA to help find the right coverage for them, along with some much-needed savings. USA, what you're made of, what
the South Padre Island Convention and Visitors Bureau. Thanks also to Black Magic for all the work they do for us. We appreciate their help with this as well. Jason, terrific program today. We really appreciate it. Thank you so much for being with us. Next week, 10 a.m. on Wednesday, Elizabeth Gulick from USAA will be with us to talk about all things insurance. There's a lot you need to know as we head into hurricane season insurance-wise, and Elizabeth Gulick will be with us from USAA to talk about the insurance industry and what's happening as we head into the hurricane season. So that's next Wednesday at 10 a.m. Thanks for joining us, Bill, Jason, Alex. It's been a pleasure once again today. We'll see you next Wednesday for another episode of NTWC Live. And we okay, we are clear.